Let's talk more about the dependence of substitution versus elimination on temperature. This is actually a really interesting application of fundamental thermodynamics from your introductory chemistry courses, and it combines structural reasoning, looking at the Lewis structures of starting materials, transition states, and products, and fundamental thermodynamic reasoning, looking at things like delta G and delta S. We've seen previously that high temperatures, elevating the temperature of a reaction that contains a nucleophile or base, an electrophilic alkyl halide or pseudo halide, tends to encourage elimination. The reason for this is that the activation energy, delta G double dagger, and the free energy change, delta G naught, for elimination depends strongly on temperature for reasons that we'll see in a second. These effects are completely absent or are less important for substitution, and we can trace this difference between elimination and substitution to structural factors involved in the two reactions. Let's look at the kinetic issue first, drawing transition states for both processes and reasoning about the structures of those transition states to deduce the conclusion on the slide, which is that the activation energy is more positive for E2 than it is for Sn2. In the transition state for the Sn2 reaction, the nucleophile is approaching and the leaving group is departing. We can lay down the change in energy in going from the starting material to the transition state on a reaction coordinate diagram by drawing something like this. The transition state for the analogous E2 reaction here is significantly different. In the Sn2 transition state, we see that two bonds are undergoing change. The carbon leaving group bond is breaking, and the carbon nucleophile bond is forming. But in the E2 process, we see that four bonds are involved. A bond is forming between H and OH, the CH bond is breaking, a new CC pi bond is forming, and the carbon leaving group bond is breaking. Furthermore, the E2 transition state has this strict requirement of an anti-relationship between the carbon leaving group and carbon-hydrogen bonds that's not present in the Sn2 transition state. For these reasons, the transition state of the E2 process is significantly higher in energy than the transition state associated with the Sn2 process. This makes the activation energy for the E2 process considerably higher as well. One of the reasons heat encourages elimination in this case is that it enables more molecules to surmount the higher activation barrier, or delta G double dagger, for E2 elimination relative to Sn2. But this isn't the only thing going on. There's an important thermodynamic effect occurring as well. Consider the byproducts of the Sn2 and E2 reactions. Sn2 produces only the organic product and a byproduct that's the conjugate base of the leaving group. This is two molecules on the product side in total. We can lay down the thermodynamic energy change from reactants to products for Sn2 doing something like this, noting that because this reaction converts two molecules of starting material to two molecules of product, that delta S overall for this process is near zero. There's not much entropy change that goes on. The situation is very different for the E2 reaction. Although here we also produce the conjugate base of the leaving group, we also produce the conjugate acid of the base, here H2O. This is three molecules. For E2 elimination then, because we're going from two molecules to three molecules, we should predict, all other things being equal, that the entropy change here is going to be positive. We're generating more molecules than we started with. What does this mean for delta G for substitution and elimination? Well, remember, the free energy change of a reaction is equal to delta H minus the temperature times delta S. This means that if the entropy change is zero, as it is roughly speaking in the Sn2 case, then what we can say about delta G is that it's temperature independent. However, in the case of the E2 reaction, because the entropy change is positive, increasing the temperature is going to decrease or make more negative delta G. So now let's lay down the thermodynamic energy change involved in the E2 reaction, and let's say we're at a very low temperature that minimizes the impact of that delta S term for the elimination on its free energy change. Higher temperatures will tend to pull down or make more negative delta G until a critical point where the favorability of elimination passes the favorability of Sn2, which is completely unaffected by this temperature change. And so at some point, E2 becomes more favorable than Sn2 at some critical temperature. At temperatures beyond this point, we should expect the E2 reaction to dominate over Sn2, and these can be very reasonable, very moderate temperatures. Things like 50, 70, 80 degrees Celsius are often enough to favor elimination over substitution, for example, for secondary substrates. And the last thing I'll mention is that because this whole discussion is wholly thermodynamic, the exact same ideas apply to Sn1 and E1, which don't differ from Sn2 and E2 really in the fundamental natures of their reactants and products, only in the route to get from reactants to products, or the reaction mechanism.